Hello, guys.
Hello.
Hi, Lisa. So I don't know if you can tell, but today I'm at DVC. And I decided to come to school to make sure that I can send you guys recordings of what happened on Tuesday and hopefully very quickly load today's session online as well. So one of the things I wanted to pay attention to today was the following. I want to screen share the Zoom window. So as you can see, this is the lecture from April 28th. So that was our Tuesday session. So I'm copying the shareable link. And I'd like to send it to you via chat. So I'm sending this to everyone. And when I open it, it actually pops for me into a video screen. And the video screen plays. So you'll notice how this is a little bit longer than an hour. And you'll notice the lights of Paris we had on Tuesday. And it's kind of like la la la. Like if I go to okay, can you guys open it or not? Are you guys be able to open the link I sent you and do the same thing? Watch the same video? So, hey, Alan, how are you?
Good, how about you?
Good. I don't know if you noticed, but I'm in my office at DVC today.
Oh, sweet.
So if you're having difficulty, we could meet in the, off campus. I have to meet people off campus. I can't meet people on campus.
Okay.
That would be a violation of the campus shelter in place. So I can work from here by myself and keep myself isolated even from myself.
Mm-hmm.
But the school has asked us that if we do come to campus to do some work, to not interact, to not bring students to the campus because of the campus is officially closed, and we want to have protect the campus from any liability of the sort or kind. But so as long as we practice social distancing, we can meet anywhere. I think I sent you an email reply yesterday about your request. So
Yeah, I saw it earlier today.
cool.
I messaged you Tuesday, but I don't think you saw that message. But that's fine.
Yeah, no, I haven't seen a text message because I sent you a text number, right?
Yeah, no, oh no, it was an email on Tuesday, and
I know,
I just
but
got your
but I
text.
replied to that one with a text message.
Yeah, I saw that today.
Okay, and so just send me a text message with like when you can meet today or tomorrow, okay?
All right, thank you so much.
My pleasure. So did that link, did the first link work that I sent you? That I sent you guys?
It's not working for me.
Yeah, okay, so we're gonna try to make that work. And how about anybody try the second link I sent you?
None of them really work.
Neither works? Okay. So if I copy the invitation, that's for the lecture time. That's for upcoming. Let's look at recorders and recordings. Okay, so what I'm gonna do is I'm gonna download this recording. As you can see, it's a pretty large recording. That's kind of like the problem of doing it the way they want us to, because the video is 271 megabytes, and then if you put in the screens and the chats, it's over 300. It's 300 megabytes. So I'm going to download it to our Canvas page, and then you can download it and view it, and either delete it after you view it or whatnot. Okay. In the meantime, what kinds of questions do you have today? Do you have any questions particularly that you'd like me to explore? Or should I head right into our...
Can we please do like lab 7, like questions 7 and 8? If that's
For
possible.
sure.
Thank you.
Any lab 7 question request in particular?
In the chat, it says question 4, lab 7 from someone.
Oh, I haven't looked at the chat. Oh my God, I'm so old. Let's see what happened here in the chat.
Okay, all right, that's fine.
Question 4. How's that?
Okay.
That's question 4. So the question for each of these 4 parts that we're going to work on is, what is the percentage of the normal
Okay, that's
model?
fine.
Of the
Yeah, we'll just
standard
get it.
normal
We'll get it in now.
What percent of the standard normal model is found in each region of the bell curve? So this bell curve here. And as you can see, this is called a standard normal, which means that it's about z-scores. So the values being measured horizontally have a mean of 0 and a deviation of 1. And you just want to use z-scores bigger than 0.6, for example, or smaller than 0.5, or between 175 and negative 195, or bigger than 1.7, and at the same time smaller than minus 1.7. So that's what this absolute value here means. Okay, so I'm going to open StatCrunch. And again, the parts for this problem cover areas or ranges of Z that are either bigger than 0.6 in part A, smaller than 0.5 in part B, between
Sorry, we can't
minus
see.
1.95 and plus 1.75. So I'm reading the same problem here. I'm reading the problem right there. And then it's either larger than 1.7 or smaller than negative 1.7. Okay. And I'm gonna now go to the StatCrunch window. Can you see the StatCrunch window? Everybody okay with that? With the StatCrunch window? Rawa, are you doing all right so far?
Yes.
Can you confirm? Okay. So these are my 4 parts to the question 4. So I'm going to go stat, calculators, normal. Stat, calculators, normal. And then I'm going to apply each of these ranges to get the 4 answers there. So the first part is that I'm looking at z-scores bigger than 0.6. So all I'm going to do is change this to 0.6. And instead of less than, I'm going to go bigger than. And so the graph is going to look like this graph here. Then I'm going to open another calculator, another normal calculator. And in this case, I'm going to be looking at less than 0.5. So part A looks like the graph on the top and part B like the graph on the bottom. And the areas are respectively 27% and 69%. Did that make sense, Rawa? So
Yes.
all I have to do is go back to the problem and notice how the graph for Z greater than 0.6 is B. And the area is in percentages. So instead of writing it as 0.2743, I'm going to take the decimal and move it to the right 2 spaces. Sorry, move it to the right 2 spaces, not 3. So this 2743 and this picture here correspond to a z-score greater than 0.6. The z-score is positive, which means that you're looking at values above average. And from 0.6 forward, above 0.6 is this gray zone. And I got that from looking at StatCrunches at this graph. Where you put 0.6 here, you look above 0.6. And so the percentage of the area here is 27%. And you do the same for all 4 parts. For less than 0.5, we did that one. So when we go back to the homework, below 0.5, where the area is 69%. Part C says that you're starting at a negative z-score and you're stopping at a positive z-score. So it has to be graph D. Sorry, yes, part D here. And then you got to figure out how big this area is. So to do that, we're going to go back into StatCrunch from the assignment. And there, we're going to use the calculator in what's called the between mode. So when you change from standard to between mode, you're able to put in a lower limit cutoff point, as well as an upper limit cutoff point. And the area is 93.44%. In the last part is using something called an absolute value function. You might not have seen that in a while since your days of algebra. Maybe even then you didn't really spend a lot of time looking at absolute values. So when it says that the absolute value of z is more than 1.7, it means that z can be bigger than positive 1.7 or smaller than negative 1.7. So to do that kind of a problem, we just put minus and plus 1.7, and we get the red zone here, which is 91% of the curve. But we're not really interested in the interior of the model. We're interested in what are called the tails of the model, the extreme values that are less than minus 1.7 and more than positive 1.7. So if the red zone is 91%, the white zones are 9%, because the whole curve is 100%. So we use the rule of complements from probability from chapter 5 to find our answer on the ends of the distribution as opposed to on the middle of the model. So I'm going to take that 9%. Does that make sense, Rama?
Yeah, I was just having trouble with the percents, so that helps.
Oh, cool.
I didn't
Awesome.
know that it
So
was.
it was just the rounding. Perfect.
Thank you.
Good review of using the normal model anyway. But I'm glad that it was just a format issue of the percent. Question 5 is identical. It's just more of the same. So I'm going to skip it and go to question 6. In question 6, what we're doing is we're still using the standard normal model. But instead of being given z-scores, we are given probabilities or areas of the model. And these areas are in either the highest or the lowest parts of the model, or the middle. Okay. So in that case, we're just gonna, instead of being given ranges of z, we're given areas of the model. Highest 35%. then it's the highest 55, then it's the lowest 95, and then it's the middle 80. Okay. So those are the four problems. Let me switch into StatCrunch. And then what we're figuring out here is what kind of a z-score range are you looking for? So you're going to be looking for a z-score range that is above a certain marker, where it says highest. When it says lowest, you're going to be looking at z-scores below a certain marker. And what's in the middle, you're going to see z-scores that have two cutoff points, a lower cutoff point and a higher cutoff point. Okay, so our answers will take the form of either one z-score or two different z-scores. And we're just looking for that magic number that makes these cuts. Any questions about that? So in
Well,
a
that makes
problem
sense.
like this, I'm gonna go to standard, to the standard calculator for the first three cases, because the standard calculator covers either greater than points or less than points. And the only time that I'll use the between calculator is when I want two cutoffs. And that's when I have the middle 80%. Okay. So in this case, the numbers are minus and plus 1.28. Because that's that range from minus 128 to plus 128 cuts off 80% of the model in a between calculator. And then when you use the standard calculator and you're looking at the lowest 95%, this lowest 95%, you put a 95% there and then you look below it, you look to the left of it. So think of the less than sign as an arrow that's pointing in the lower direction. And that gives you the right z-score. So the z-score below 1.645 gives you the lowest 95% of the model. Then the highest 55 would be the highest 55%. So that has a z-score that's near 0 but below. And the highest 35% has a z-score like that. So once you have the four answers, you can just plot them back into the models and you can look at the different areas and make sense of them.
Alan?
Yeah.
Can you just review real fast again? In D, how'd you get to the 128?
So for D, I'm gonna not use the standard calculator because when I put the calculator in standard mode, I only get one place to cut off. So I don't get a middle part. To get a middle part, I go to the between calculator and I set the area to the desired area. In my case, it's the middle 80. So that's how I got the minus and plus 128. What would be the middle part in your question 6? What was this 80% in your
Mine was also 80.
Okay, cool. So
Yeah.
then that's how you know you have to go from the mean. You need to go back below it by 1.28 deviations, and you need to go above it by the same amount so that you get a symmetrical area of 80%. And then the white parts are 10% each so that you can account for the whole bell curve of 100%. So this red part is the 80%. And that's 10 and that's 10. And the cutoff points are at 1.28 deviations below average to 1.28 deviations above average, because we're talking about z-scores. So in this case, we're going from a given probability to a given z-score range. In the previous problem, we were given the z-score range and then we calculated the areas. So as long as you know one of these boxes down here, either the area or the range of z, you'll be able to solve for the other one. Okay, so now I'm just going to go back to my homework and look at what I'm doing. Highest 35% looks like this. And the z-score that I'm looking for there is 0.385. The highest 55% looks like that. And I'm going to have a negative z-score there. So I put minus 0.1257, 126. Then the lowest area looks like this because it's below the marker. The z-score is 1.645. And then the middle area looks like that, with just the center being covered or being shaded. And this is minus 128, and this is plus 128. Any other questions or suggested problems to work on?
Can we
Anything in
do
the chat?
7.4?
Which one, pardon me?
This one that we're on the screen right now?
This one? Okay.
Yeah.
So this problem is an application of the normal model. Okay, so this is lab 7, question 7. And what you have is what's called a compound model. So the model is called time. And time equals the time from the first swimmer plus the time from the second swimmer plus the time from the third swimmer plus the time from the fourth swimmer. So that's what we call a compound model. Because we're compounding 4 times into 1. And the strategy when you have any model that is made up of parts, the strategy is a 2-part strategy. So in one part of the strategy, what we're going to do is we're going to find the mean and the standard deviation. And in the other part is we're going to do the probability calculations necessary. So those are always the 2 steps to follow.
Uh-huh.
Okay, so this is step 1 always. And this is step 2. So how do we find the mean? How do we find the mean and how do we find the standard deviation? Well, we learned that in chapter 6. In chapter 6, we learned how to combine uncertainties so as to create a model like here. And the way we do that is with the following 2 formulas. Okay, so here are the formulas for expectations and deviations. The expected value of time is going to be equal to the sum of what are called the column that's called the mean in your problem, and the standard deviation of time is going to be equal to the square root of the variance, and the variance equals the sum of the variances of each time.
Mm.
So these are the 2 formulas. So I'm going to copy this. These are the 2 formulas that I'm going to use in StatCrunch.
Uh-huh.
This is the generic version of these formulas that I use in StatCrunch to do step 1.
Okay.
And then to do step 2, I'm just going to call on the normal calculator. And that's going to be for part B.
Okay.
So in this case, I'm going to do stat, then calculators, then normal. I'm going to set the mean and the standard deviation to the step 1 numbers. And then I'm going to calculate the probability of some normal range to get some area that is actually equal to a percentage, equal to a probability.
Okay.
So those are kind of like our 2 steps to do the math, so to speak, in StatCrunch for the yellow step and for the blue step.
Mm-hmm.
That's a strategy. And that's a strategy in every problem of this form.
Okay.
So let me call the data into StatCrunch. So I'm going to go back now to the problem. And the way I call the data into StatCrunch is I have a copy icon right there. So I click on it and I open it in StatCrunch. I hope you can see it.
Yes.
Cool. So I'm going to go first data, compute. And this time I'm going to compute not 1 expression, but 2. I'm going to bring the expressions that I copied for the average and for the standard deviation. And so I'm going to call this E, and I'm going to call this ST D for standard deviation. And compute. Okay, data, compute, multiple expressions. So I'm going to take the sum of the mean, and that's my average. And then my deviation is going to be that. Those are the only two formulas I need, compute. So there they go. That's the average and that's the deviation. So I'm going to move those two answers to my tiled window. You can see that I just put the two answers there. And now I'm gonna check the answer. That has to be right because I use the right formula, so they can't be wrong if I use the right formula.
Yeah.
And then in the second part, it says the team's best time this season was a little over 3 minutes and 17 seconds. And the way you list that in seconds is as a 197.18. So then the question is, what is the probability that they will beat that time? So what's the probability that the time that you run the next race in is less than 197.18? So that's called beating the fastest time. Going faster means running the, swimming the relay in less time.
Yeah.
So that's what I'm gonna go back to StatCrunch now to do the math for that. So that's the blue box in the notes on the board. Stat calculator is normal. I'm gonna set the mean to the average. I'm gonna set the deviation to the dev, because that's what I call the mean and the standard deviation. I call them average and dev. So I type them exactly like I call them. And the software will know that the mean is 197.56. And it will know that the standard deviation is 0.43335997.
Yeah.
And then I go here and change this time to 197.18. And I get the look of the model, which is their best time this season so far is a 197.18. And the chance that this particular relay is done faster than that time is 19%. So I'm going to go back to the homework, and I'm going to know that this is 0.19. It wants 4 decimal places, or 3. So that's what I got in StatCrunch. And it's got to work because it's the right thing.
Hey, Professor. You
Yeah.
think you could go over how you got the standard deviation again?
For sure. So what we said in chapter 6 was that when you have a compound model, a model that's made up of several parts, the way you treat the expectations is really simple. The expectation of one part, the expectation of time, in this case, is going to be the expected value of x1 plus the expected value of x2 plus the expected value of x3 plus the expected value of x4. Okay, so there's no secret to that one. It's pretty straightforward. Because time happens to be the sum of the 4 parts. The expectation of the sum is the sum of the expectations. So that's what that means. The difficult challenge is with the standard deviation, because a standard deviation usually requires us to square the differences from the mean, because differences can come in 2 varieties. They can be below average or above average. And so we square to basically account for any variation, whether it's above or below average, without having them cancel each other out just because one carries a positive sign and others carry a negative sign. So we square the whole thing first. So the standard deviation of time in this sense is really the square root of the variance of time. Okay. And then we have to calculate the variance of time. And the variance of anything that is made up of parts is really the variance of each part, if we make an assumption. The assumption has to be that each component is independent of the other component. So I have to make an assumption that the swimmer who is swimming the backstroke and the swimmer that is swimming the breaststroke and the swimmer that is swimming the butterfly stroke and the free stroke, those in freestyle, those 4 people are not influencing each other's performance. And we call that assumption the assumption of independence that you see here. That no swimmer impacts the other 3 swimmers' times. And each swimmer's time is a normal distributed model. So the sum of the 4 components will be also normal. And that's why I'm able to use the normal model. So when I combine the formulas for the variance being the sum of the variances of the 4 components, with after I calculate the variance, taking the square root of that, what I end up with is with the formula that you see down here, which is taking the square root of the sum of the variances. Okay. And the way I actually do the math in StatCrunch is precisely in that way. So when I go back to StatCrunch, the way I got this deviation here was I took the standard deviations, which are this column, and I squared each standard deviation first. So I took 0.23, 0.22, 0.24, 0.17. Each one of those got squared. After each one of those got squared, the whole group got added together. So I added together the square of each of these 4 items, and that's called the variance. And then to get the standard deviation, I take the square root of that sum of squared deviations. And that becomes the standard deviation for the whole model. Did that make sense? More or less?
Yeah, that makes sense.
Okay. I didn't know if who asked the question, but I'm hoping if you have any questions, feel free to ask again.
Yeah, thank you so much. That was great.
Okay, cool. So where that becomes super useful is in your, you have another problem like that. Called a serial problem, as in Lucky Charms. As in this problem here. It says the amount of cereal that can be poured into a box varies that can be poured into a small bowl varies with an average of 1.5 ounces, give or take 0.3. In a large bowl, the large bowl holds more on average with a higher variation. Lisa opens a new box of cereal. Lisa, what's your favorite cereal?
I don't really eat cereal.
You don't eat cereal?
Not too
How
much.
about you, Joey? Do you eat cereal?
I like Frosted Flakes.
Kellogg's Frosted Flakes?
Yeah, simple.
It's simple. Man, I like chocolate cocoa. I like Cocoa Puffs because they're like basically like chocolate corn pops, but it's, I don't
Those
know.
are good too.
I mix them with like Fruit Loops and I do all kinds of crazy stuff, man. I put like a couple of ounces of Bailey's, and it's just, anyway, it's a good cereal to have at night. It's like a nice dinner with Bailey's and stuff. So, so a student opens a new box of cereal and pours one large and one small bowl. Then here comes the question. Suppose that the box of cereal also has a certain amount when it's brand new and a certain amount of variation, because the pouring process, you know, you can imagine, you take a Frosted Flake and, you know, even a machine can miss and either put a little too much or a little too little cereal in the box. Okay, so the first thing they ask you is find the expected amount of cereal left in the box. So I'm going to call that C lit B. Okay, amount of cereal left in the box. And C lit B is new box minus large bowl minus small bowl. So that's the model. The model is not a sum, but a subtraction in this case. Does that model make sense?
Yes.
Okay, so when I try to calculate the expected value, okay, when I want the expected value of the cereal left in the box, I need to calculate the expected value in the new box. Then instead of adding, now I got to subtract what is it that I expect to see in the large bowl. And also what is it that I expect to see in the small bowl. To get the answer. So here's what I'm going to do. I'm going to go back to StatCrunch. And instead of swimmers, I'm going to put here components. And this is going to be the new box This is going to be the large bowl, and this is going to be the small bowl, and this is going to be the cereal left in the box. And I'm going to change these means. And I'm going to change these deviations. And I'm going to change all this stuff. So the means here are 16.4. That's the new box. This is negative 2.3. And this is negative 1.5. So why did I write these as minuses instead of positives?
You're subtracting it out of the box total.
Correct. And then I remember that this was 0.1, 0.4, and 0.3 respectively. Those were the deviations from the problem as the problem was presented. And now I'm going to calculate these same two formulas. And when I do, I'm going to get the average left over in the box is 12.6. So when I go back to StatCrunch, from StatCrunch to the problem, this is going to be 12.6. And then what's the standard deviation? Well, that's 0.51. So I got those two answers in exactly the same way as I got the answers before.
Yeah.
That's what's nice about having these formulas already preset as a way of thinking, that any model that is a compound model, you put the components in and you just have to make sure you interpret the numbers correctly to get the mean and the standard deviation correct.
Yeah.
And once that happens, then the homework becomes a few minutes long rather than a ton of time long. So what is the assignment? Next, it says, if the weight of the remaining cereal can be described by a normal, what is the probability that the box still contains more than 13 ounces after the first pour? So what you want to know is, what is the probability that the amount of cereal left in the box is greater than 13 ounces? So I'm going to go back to the model, back to my stat lab. And now that I have the mean and the deviation, I'm going to go back to the normal calculator that I had even before, that I had already opened. And notice I don't even have to do anything to the mean and the deviation because they're called the same. It's just that the numbers are now going to be different. And I'm going to go greater than 13. So what is the chance that after I pour a big bowl and a little bowl out of the new box, I have more than 13 ounces? The chance of that is 0.216, 21%. So over here, I'm going to go with 0.2164.
I'm sorry, can you do that real quick again? Thank you.
You mean that? You mean showing the calculator?
Yeah, how did you get the last question?
Okay, and the last question was a normal model, right? So I opened the normal calculator. Stat calculator is normal. Then I set the mean to the mean that I had calculated. So I can put 12.6 here. And that's fine, it'll work fine. And I can put 0.51 there and then go more than 13 and I'll get the same answer. But instead of putting the mean, I could also call this small case AVG. And I can call this small case dev. And by calling them their generic versions, if I have another problem with a different data set, they're automatically going to be adjusting to what the new average and the new deviation are. The average and the deviation that came from calculating the mean and the standard deviation of the whole thing. So once you have the probability, you just pass it to the assignment. And you're done. So that's how you go from a compound model to a normal calculator and use the normal to estimate that. Do you guys have any other questions in the lab, or let's go to the exam for a moment. So I'm behind the scenes going to exam 3. I'll open it shortly. And in exam 3, you have this question, question 10. Can you see exam 3, question 10? I'll assume the answer is yes. And this is called the coffee and donut problem. And I think we did this problem on the Tuesday session. Is that correct?
No, we didn't. I think you referenced the PowerPoint.
Ah, okay. So you guys know about the PowerPoint slideshow.
Yes, and I actually have a question on that.
All right, cool. So this question actually has 3 models, not 1, but 3 models. Okay, so so can you see the 3 parts or not? Okay, let me so those are the 3 parts. And how many of you have tried this problem yet? Or who has not tried? Can you guys give me a sense by telling me through chat? Okay, so most of you guys haven't. Okay, so I'll go slowly then and read it. But just remember that if you, for exam 3, question 10, there is a template solving this question in Pearson. Under course tools, document sharing. Exam 3 module. And it's called the coffee and the donut problem .pptx. Okay. So let's see what we've been doing in action on exam 3. This is a model about selling coffee and selling donuts. So the ingredients are coffee and donuts. Are you guys okay with that? Can you see everything, by the way, in the window or not? All right. So it says here in this question, they have a certain coffee shop where every customer who shows up buys coffee for sure. So the uncertainty is not whether they're going to buy coffee or not, it's whether a person walks in the store or not, because they could not, somebody may opt not to go in for coffee. Now, some of the people who buy coffee also buy a donut. So you have two parts to this random story. You have capital C, which stands for coffee. And capital D, which stands for donut. The shop owner believes that the number of cups he sells every day follows a normal model, and the average is 310 cups of coffee a day, give or take 19. So the way we shorthand that is we say that C follows a normal model with 310 average and 19 deviation. And D follows also another normal story with an average of 130 donuts per day sold, give or take 14. There's something special about these two products. The number of donuts sold each day is independent of the coffee sales. So the key there is the word independent. C and D are independent of each other. Okay. So I'm going to take all that language out because now we have it shorthanded here. Okay. So this is exam 3, question 10. And we have two parts to this model. There they are. We also know that C and D are independent from each other. That's going to come in handy because if we need to combine them somehow, when we calculate the standard deviation, we need to make sure that they're independent so that we can add the two variances. Like for example, in part A. In part A, the shop is open every day but Sunday. So what's the model for A? The model for A is selling coffee cups in a week. So if you're assuming that every day is independent of every other day, what is the probability that the sales from 6 days, the coffee sales from 6 days, are over 2,000 cups? So that's the shorthand for model A, and that's the probability that you're calculating. So what are the 2 steps that we need to do to calculate this? So step 1, we need to figure out the expected value of 6 times the value of C. And we also need the standard deviation of 6 times the value of C. So that we can then do step 2, which is to figure out the probability that model A is more than 2,000 cups of coffee in a week. So those are step 1 and step 2 there. What is the model called model B? Model B is going to be called the profit model. So model B, AKA profit, is going to be the 50 cents you make every time you sell a cup of coffee, plus the 40 cents you make every time you sell a donut. Okay. So that's the model. Your numbers may be different. You might not get 50 cents and 40 cents, but other than that, the structure of the model is the same. And again, coffee and donut sales are independent of each other. So it'll be nice when we do step 1 of calculating the mean and the deviation of profit. And then the question is it reasonable to expect to have a day's profit of more than $300? So can profit be over $300? Well, to answer that question, I got to answer what is the probability that profit is above $300 a day. And so I have to explain it using the same tools, the same 2 steps. And then the third model is, what is the probability that on any given day, he'll sell a donut to more than half of the coffee customers? So what is model C telling me? Model C is asking, can I make coffee? Model C is, can I sell donuts to more than half of my coffee buyers? So that means that model C is D minus 1/2 of C. And the question I'm interested in is really, what is the probability that model C is greater than 0? So that's going to answer the question of whether I can sell a donut to more than half of my coffee customers or not. So those are the three models in the three questions. And every model is answered by doing the same two steps: calculate expectations, calculate deviations, calculate the expected value and the standard deviation. And step 2, figure out a probability. Or chance. So the strategy is always the same two steps that we did in the problem with the cereal box and the small bowl and the large bowl, or that we do with the swimmers. There's another one where you assemble a bicycle in parts. Same two steps. So here go the steps. What is the expected value of model A? Model A is 6 times the sales of coffee. So that's just 6 times the expected value of coffee. So that's 6 times 310. So that's 1,860. What is the standard deviation of model A? Well, that is the square root of the variance. And the variance is the variance is 6 times the 19 to the power of 2. So I square this. 19 times 19. I think that's 361. And I multiply 361 times 6. And that's 1,800 and something. And I take the square root of that, and I get a number. And since it's kind of complicated, I'm going to just take it, copy it, go to StatCrunch. Okay, so I'm going to go to question help StatCrunch. And go data compute expression. And that's my standard deviation. My standard deviation according to this is 46.54. $46 47 coffees, give or take, in a week of standard deviation over 6 days. $46.54. And now that I have the mean and the standard deviation, I can then plug it into the normal calculator and get the probability for seeing a more than $2,000 cup of coffee a week Sorry, 2,000 cup of coffee week. So I'm going to go back to StatCrunch. I'm going to call this the deviation. The average was 6 times 310. And I can go stat calculator normal and try to see the chance that I sell more than 2,000 cups of coffee in a week when the mean is the average and the standard deviation is the dev. And the answer is a very small chance of that, less than 1% chance, 0.0013. So that's the answer that I plug in there. And it came from plugging in to the normal calculator. So the same step 1, step 2. Find the mean, find the deviation, put them in the normal calculator, get an answer. Same is true of the profit model, model B, and selling donuts to more than half the customers who buy coffee. That's model C. You do the same 2 steps. Find the mean, find the standard deviation, and figure out a probability or chance related to Was there anything specific about the PowerPoint slide that those of you who have seen this problem wanted to ask about? Hello. Hello. So we're a little bit out of time. I'm going to come back. I'm going to send you the link to the 1:30 session. And I'm going to stay a little bit for Satoshi because he had some chapter 5 questions. And so I'm going to answer chapter 5 questions for like 15 minutes. And then I'm going to go scavenge food. I'm going to go try to kill a coyote somewhere because there's nobody anywhere near DVC other than coyotes. And I'll just have a coyote sandwich. And then, I'll come back for our time together. But any particular questions from chapter 5? Alan, you have some questions, I see, and so does Sato. So I will stick around for your questions on chapter 5. So I'm going to close for lecture time. And then I'll reopen a session after for this. I'll send you guys the link for a one-on-one meeting with the 2 of you through your inbox in mail. Anybody else staying? Anybody else want to stay?
I have a question. When do you have office hours?
I'll be back between 1:30 and 4:30 today.
Okay.
And do you want me to send you guys the link for that?
Yes, please.
Absolutely. I'll send it to everybody. It's the same, it should be the same link that I sent before. So I'm going to send it to everybody. And then, oh, the EOPS forms. Thank you, Christian, for reminding me about the EOPS forms. I need to send those. I'm going to do that today for sure. I have to. They're already tardy, and I got an email from them too saying, come on, Alan, do it. So thank you, Christian, for reminding me about the EOPS forms. Anybody else? Anything else? Okay, so give me 5 minutes, Satoshi, and I'll come back in 5 minutes, okay? Stay on board, those of you who have chapter 5 questions. Just stay in this meeting. I'll
Okay,
be back.
I'll be in. Thank you.
Yeah, don't leave. Just give me a break so that I can go scream in a bathroom or something. I'll be
All
right
right.
back. Thank you for your patience. I'm sorry to keep you waiting so long.
It's all good. I appreciate that you're staying after class.
No, no worries. So it's on chapter 5 that you have questions?
Yes, on quiz 5, chapter
Quiz
5.
5. Let me go open that.
I think, I don't know who else was waiting, but it appears that they left.
It was a young lady, but I don't think she was waiting
Oh, okay.
because she didn't send me any, Michaela didn't send me any messages about.
Okay.
Let's see, course tools. I also have to do some assignment management things here. And mhm. Okay. Cool. And now I can share screen. Okay, so I hope you can see my quiz.
Yep.
Great.
That's one I had issues with. It wasn't mine, but it's definitely like one of those problems I was certainly confused about.
Okay. Fortunately, this table, I hope you can see it.
Yeah.
This is actually just plain data. And so, which is crazy because this is like a chapter 1 issue, right? And so this probability space is data telling you that there's 7 houses total because there's 7 rows.
Right.
So that means that every probability in this thing is going to be a probability out of 7.
Right. Okay.
So for example, when it asks what is the proportion of homes valued at $500,000 or less, that would be 3 out of 7.
Right. So do we just write 3 out of 7, or do I have to decimal it and all that?
You should decimal it. So it's like 0.43, 0.4328, something like that. It says round to 2 decimals, so it's 0.43.
Yeah. Oh, that makes sense. Dang.
And then in part B, the difference between part A and part B is that in part B, you have some conditional probabilities.
Mm-hmm.
So for example, the question is the number of bedrooms and the property values independent? Or is the number of bedrooms and property values not independent? And the answer is not independent because the probability that a house is quote unquote cheap under $500,000 is 0.43. But under $500,000, given that it's a 3-bedroom, if you notice, there's only one 3-bedroom house.
Mhm.
And it's not under $500,000.
Right.
So the answer there is 0 out of 1, which is, again, just 0. And then if you look at the 2-bedroom houses,
There's none that are below 5.
exactly, there's none out of 3.
So 0.
There's 3 2-bedroom houses. And so none out of 3 is 0. And then every house that is a 1-bedroom is cheap, and every house that is no bedrooms, like a studio, is also cheap. So because the probabilities vary by the number of bedrooms, the number of bedrooms and the probabilities are not independent.
And the probability for, I'm just kind of checking here, but the probability for under 500,000 with 1 bedroom, I see that there's 2 out of the 4 possible houses. So I'm just going to go with 0.5, and that would be correct, right?
Where
me,
are you seeing? Are you looking at the number of bedrooms column?
Yeah. For my data set, it has 4 out of the 5 that has, 4 out of the 7 are under 500,000.
Yeah, but what about the one? How many houses have 1 bedroom in your data?
2. And both of them.
Both are under 500,000, right?
Yep.
So it's 2 out of 2, so it's 100%.
But wouldn't, okay. But wouldn't it count the houses that are, okay, I see. So it doesn't count the houses that don't have a bedroom under 500.
Right, because it's only for the 1 bedrooms. It's conditional on a house having a 1 bedroom, so it's 2 out of 2.
I see. So then for the next one, it asks kind of the same question, but for under 500 without a bedroom.
Like a studio,
A bedroom, yeah. So I have
1 out of 1.
I'm confused with the 1 out of 1. Because there's 2.
Can you share your screen with me?
I'm on my phone, but I could just flip the screen around. Can I? I don't think I can.
No, but if you tell me how many houses have 0 bedrooms in your list?
2.
2. And what are the prices of those 2 houses?
One is 172, and the other one is 218.
So therefore, it's 2 out of 2. Both are under 500,000.
Ah, I see.
So since it's 2 out of 2, it's 100%. So my answers and your answers should coincide. 0, 0, 1, 1.
Yeah.
And then the generic answer is 0.43 because it's 3 out of 7. Any other questions?
Yes. I believe I had I had 6 of them completed. I should
Okay.
have 4 that were
Excellent.
so this one is the question about professional polling organizations.
Okay, I'm right there.
Yeah, you are. So I got the numbers. I was just having an issue with the independent and the disjoint stuff.
Okay, so disjoint are sets that do not match. Okay, so I'm gonna copy this to a clipboard, and I'm gonna put this in a board. Okay, so these are the 4 types of data you got.
Yep.
And I'm gonna draw a box. And this box is everybody in the population. So this is all people. Now, some people don't have phones, right?
Yep. Some people don't.
Okay, so I'm gonna have some people who don't have phones. So those are people without phones. Now, there are people who only have cell phones. So they're old-fashioned, so I'm gonna put stars next to them.
Okay.
And they make up 37% of the whole population.
Yeah.
They're stars. They're like modern tech people. They only have cell phones. They don't have landlines. So I'm gonna cut off about 1/3 of the blue box. And I'm gonna color them in kind of like the closest thing I got to a gold color.
Okay.
And I'm gonna color them all. So all these people are the 37% of people who have cell phones only.
Yes.
Clearly, the X's are disjoint from the gold because the X's are people without phones.
Mhm.
In fact, the X's don't have any phones, so they don't have landlines either.
Yes.
Now, there are some people who have both landlines and cell phones.
Mhm.
So those are wishy-washy people. I'm going to Barney them.
Yep.
And they make up 27%, which is like a quarter of the whole data set. So that's about a quarter, and that's a little less than a quarter, a little more than a quarter.
Mhm.
So those people have both cell phones and landlines. Now, why are they, the purple, disjoined from the orange?
Is it they have nothing to do with each other?
Right. They see the orange people don't have landlines.
Right.
So
And
they
you can't-
can't overlap. So
Right.
they have to be separate, disjoint.
Okay.
Then there's 19% of people who only have landlines. So I'm going to call those people green. So those people, those 19% are 1/5 of this whole box. About that much. That's about 1/5 of the whole blue box.
Mhm.
Because 19% is almost 1/5. It's a little shy of 1/5.
Mhm.
And the last group is going to be people who are like secretive
Yeah.
because they're unlisted.
Mhm.
So they only have a landline and they're unlisted, and they're like 10%. So it's like 1/10 of this. So
Yeah.
they're here, and there's like here.
Yeah.
The point is that none of these 4 groups have anything in common with each other. So they're all disjoint.
Okay.
And when I take into account all that, then I've taken into account everybody.
Okay.
So if I'm thinking of 100% of everybody, I got the 37% who have cell phones only, the 27% who have landlines and cell phones, the people who have landlines only, no cell phones, and they are listed in the phone book, and then there are people who don't have a phone book listing. So that's 28%. 28 plus 27 is 55. 55 plus 37 is 92. So there's 8% of people who don't have phones at all.
Yeah. Okay.
So the group that's no phones at all is 8%. So now I've cataloged everybody thanks to this Venn diagram. So now I have the probability space, so to speak. Now that I have the probability space, I have a question here, question A. And question A is, what is the probability that a randomly selected adult has a landline? Well, there's 27% of people who have cell phones and landlines. Then there's 19% that have landlines and are listed, and there's another 9% who have landlines and they're not listed. So that's 55%. So that's part A.
Mhm.
And it says, what's the probability that an adult has a landline given that he or she has a cell phone? So in this case, you want the probability that someone has a landline given that they own a cell phone. And so that's called a conditional probability. And the formula for a conditional probability is the probability that a person has a landline and a cell phone divided by the probability that a person has a cell phone. So that's the formula.
Oh.
So then landline and cell phone. Landline and cell phone are 27%. Those people have cell phones. But there are also other people who have cell phones. The 37% have cell phones too. So to get this answer, I'm going to have to divide 27 by 64 to get the answer. Does that make sense?
Yes.
And then the first one was, what's the probability that someone owns a landline? And that was the people who have a landline only, and then people who have a landline and a cell phone. Okay, so that was that. And then the generic questions are having a landline and a cell phone independent? And the answer is no. And that's because the probability of having a landline depends on whether a person has a cell phone or not. In other words, this answer that you get from dividing 27 by 64 is not 55%. Since the part A answer and the part B answer are different, and they cannot be independent. They have to be dependent.
Okay.
And then when it says, are cell phone and landline disjoint, the answer is no, because you could have both.
Right.
In fact, we know that 27% of people have both.
Yes, they sure do.
Any other question?
I believe so. It's the one on the lie detectors. Lie detectors are controversial instruments.
Okay. So they tell you that 92% of people are trustworthy. That means that 8% are not.
Yep. I got to there. That's where I got to.
Then before that, they told you that a polygraph can detect 58% of lies.
Mm-hmm.
That means that a polygraph has a 58% chance of catching a dishonest person. And a 42% chance of being fooled by a liar. And unfortunately, 12% of the time, the lie detector finds trustworthy people incorrectly saying that they lie. And so 88% of the trustworthies are correctly identified as trustworthy people by the polygraph. And I got the 12 and the 58 from the problem.
Yep. Yeah, I just didn't know where to like put them because I was like really not understanding how the wording of this question was killing me.
Got it. So there are two kinds of errors here. There's something called a false positive and a false negative. The 12% is the false positives.
Right.
Because those people, the polygraph says they're lying when they really don't lie. And the false negatives are the people whom the polygraph says they're not lying when they actually are because they're dishonest.
Gotcha.
And the two correct things are the 88 and the 58. So then when it asks you, what is the probability that a random job applicant will be an honest worker who is cleared by the polygraph? An honest worker who is cleared by the polygraph. So it's honest and cleared. Their cleared is 88%. Their honest is 92%. So you just multiply the two parts. Honest, cleared.
So we just multiply the trustworthy people, which is for me 0.96, by the false, what is this, the false negatives, the false positive?
No, by the true answers, by the 88%. Because when the polygraph says that a person doesn't lie, that's, in that case, the polygraph is right. The trustworthy people don't lie.
Right.
So you just multiply the 92 and the 88. And in this case, what's the probability that a job applicant who is rejected was actually dishonest? So what's the probability that you have a dishonest person given that they were rejected?
Rejected by polygraph, actually dishonest.
Given that they
This would-
were found to lie.
So they were dishonest, so the 0.04, and then they were actually dishonest, so 0.04.
So this is again a conditional probability. So you want the dishonest who get caught lying.
Yep.
And you want all the liars down below. The correct liars plus the incorrect, the accused as liars. So that's the calculation there. You can do the math later, so.
Yep. I just took a screenshot, so I'll be fine.
Cool. Next one.
Next one. Oh no. Not that. Not that. Okay, I was looking at some of them I didn't know, but I think after this explanations I'll get. Okay, I think I'll get most of these because you explained a bunch. So I think I'll get most of these afterwards.
You good?
I should be fine for these next couple.
Awesome. You'll also notice that your dates, everybody's dates in your section are now May 5th, not May 1st. So you have a few more days to get this done, a couple of tries.
Woo! That is very helpful.
Awesome.
Like unbelievably helpful. So great. All right then.
Cool. I'll see you soon then. Peace out.
Thank you very much. Thank you.